Okay. So today we're gonna continue the proof of the recognition principle. We'll finish that on Thursday. So we'll review what the recognition principle says, and then I'll define simplicial homotopies, and that will let us do the first third of the recognition principle. There are 3 steps in the proof, and then we'll talk about cofibrations and proper simplicial spaces, and that will help us. That will let us do the second third, and then the last third we'll do on Thursday. Okay. So yeah, so it says if you have a connected algebra over the little n-disk operad, then it's homotopy equivalent to a loop space. This is the theorem we're trying to prove, and the proof sketch is that A is going to be equivalent to this monadic bar construction. So you should think of, this as like a free resolution. And then, this equivalence, this is like scanning. Yeah. And then this step is somehow loops and geometric realization commute. Yeah, so we're going to be, I guess, today we're going to be talking about these 2 equivalences, and Thursday we'll do the last one. Yeah. Okay. And so we talked about the scanning map before, but we're going to this step is going to be about that. If you have a homotopy equivalence on the space of p simplices, then you have an equivalence on geometric realizations. Okay. So we want to prove this, and what you should think of. You should maybe think that this thing is roughly a tensor product, that in general, you should think of this as like a tensor product of whatever's in the right slot with whatever's the left slot over whatever's in the middle slot. And if you're tensoring, you tensor a ring over itself with something, that just cancels. Okay. Yeah, so we're going to prove this proposition that if you have any monad and any algebra over the monad, the algebra is equivalent to this 2-sided bar construction of monad algebra. And then the corollary, we'll just plug in the reduced monad associated to the little cubes operad. Okay. Yeah, so I guess the main tool for proving this is going to be simplicial homotopies, and I guess so. Like we want to compare, we want to compare these 2 objects, and the thing I'm pointing to in green is a realization of a simplicial thing, and the thing pointing to in purple is just a space. So what we're going to do is we're going to replace A with a simplicial space that obviously geometrically realizes to A, so then we can compare 2 objects that are sort of in the same category. It's hard to compare a simplicial space and a space. I guess like this is the geometric realization, so then you can compare them, but it's easier to, instead of comparing 2 spaces, we're going to make them both simplicial objects and then compare 2 simplicial objects. Okay. So yeah. So this definition, so this is the constant simplicial space. So this is our way of turning a space into a simplicial space. So for space X, we'll let X bullet be the simplicial space just with p simplices X, and all face and degeneracy maps are going to be the identity. And then the proposition is just the geometric realization of the constant simplicial space, just gives you X back. Yeah, what do I need to say? Yeah, I mean, basically, when you write down the formula for the thin geometric realization, you collapse everything that's in the image of a degeneracy, so you just collapse all the higher simplices down. Yeah, I mean, just if you write out the formula, you'll just observe this. Okay. So yeah, so I guess that's right. Yeah, so I guess we want to compare B, B bullet M A. We want to compare this with A. So we want to basically compare P simplices. So I guess we want to compare this, I guess, to a bullet. So what what are the P simplices of a bullet, and what are the P simplices of M? This bar construction. Well, the P simplices of a bullet are just A, and the P simplices of this two-sided bar construction are going to be M to the P plus 1 A. So I guess maybe it's better to think of it as it's like M and then M to the P and then A. So this M is that M. Yeah. So okay. So to compare these two simplicial spaces, we want like a map from the P simplices of here to the P simplices of there, and vice versa. So how do you get a map from M to the P plus 1 A to A?
Well, don't we have a map from MA to A because of the M algebra structure?
Yeah, the M algebra structure gives you a map like this, and you can just iterate that map. Right, so that gives you a map. If you parenthesize, that would give you a map MA, and then you can just, right? And then you're like, what's the map from 4MA to here? Well, we go 3. Yeah, I don't know.
I guess we have choices, right?
Yeah.
But they should all be equal because of that the property that these things have is that they're equal. Either we push together two M's.
Yeah. So you're saying like, hey, we could also just compose the two M's to get here.
Yeah.
Yeah. Or or the whatever. Parenthesize like this, and like that. These are the same maps as exactly associativity. Yeah. So there's a unique map, but there's lots of different ways of describing it. Or at any stage you could just compose any of the M's or compose an M with an A. Yeah. Okay. So yeah, so being an M algebra gives us this map, which gives us one of these maps that we wanted, I guess. Yeah. So we're trying to construct maps in each direction and then prove that the compositions are homotopic equivalences on geometric realizations. Okay, yeah, so the answer is just multiply, and you can either just use the fact that A is an algebra, or you can also use that M is a monad. Okay, so how do you get a map in the other direction? Yeah, so Michael says the unit, yeah, you don't even need A to be an algebra here. Yeah, you use the unit. So A, if A is any space, you have a map like this. But this map depends on the algebra structure, and what we're trying to prove is definitely going to use the algebra structure. Okay, so these assemble to give simplicial maps. So mu for multiplication, and I for, I don't know, unit or inclusion or something. Yeah. And so we want to show that these are homotopy equivalences. So we want to show that the compositions are homotopic to the identity. Oh yeah. So maybe this is out of order, but I guess I followed by mu is the identity on A, but mu followed by I is not the identity. So this is like it's like M1A. Well, that goes to like M1, or we'll say M comma A. So you should think of this as like a 1 simplex. Sorry, think of this is a 0 simplex. Let's just see. It's not the identity even on 0 simplices. Well, if you take mu of this is going to be MA. And then if you take identity of this, it's going to be identity of this. So then it's going to be like 1 comma MA. And in general, MA is not, has no reason to be equal to 1 times MA. Yeah. So one of the compositions is just the identity, but the other is not the identity. So we need this notion of simplicial homotopy to talk about how one of the compositions is homotopic to the identity. Okay. Any questions before I write down the formula of simplicial homotopy?
Yeah, I have a question. I'm a little confused with the answer to your second question. Use the unit, and I've seen we've said this before, but I really never understood it. What do you mean by that? A is a space. M is a monad, but that's a functor.
Yeah. So
where's the unit? I don't see a
so
unit.
The unit is a natural transformation from A to M. Sorry, the unit is a natural transformation from the identity to M. And that means on any object, you get a map like this. So so that gives us, in particular, so this doesn't use that A is an algebra, but this in particular gives us a map A to MA. And then you can just iterate this. Or I guess this gives us, this gives us for any space X, we get a map like that. Is that something?
Yeah. That's better. I was just not sure how to interpret the word unit. I didn't know where to look for it.
Yeah. So like in the if M comes from an operad, then the unit is literally an element in the like the arity 1 part of the operad. Like it's an element in a space. But in this sort of abstract generality, it's just it's a natural transformation. Yeah. And then and then you just iterate this, if you first apply it to like X equals A, and then you apply it to X equals MA, and then you apply it to M equals, or X equals M squared A, etc. And then iterating this would give you a map like that.
I see it now. Thanks.
Yeah, and I guess here I wrote it as if it's an operad. I guess. Yeah, I think this discussion, in order to make sense of it, you should. I don't know. Probably it's easier to make sense of what I mean by this notation if it comes from an operad. But yeah, it's in general, there's no reason for, one of the compositions is going to be the identity, but there's no reason for the other one to be the identity. I mean, in trivial cases, it could be. Okay, yeah, so we need this homotopy from one of the compositions to the identity. And so the way you get homotopies between maps of simplicial spaces is with this intimidating formula. Yeah, so F, and so if you have two maps F and G, then simplicial homotopy from F to G, I guess it's is simplicial homotopy is singular, whatever. I have plenty of typos. Is. This map is, is the data of these maps. So you have I different maps from the nth space of X to the n plus first space of Y. I guess maybe I should have called it P. P is my usual simplicial letter, but whatever. But yeah, I guess you have P plus 1 maps, or n plus 1 maps. So these are from I equals 0 to n. And then they satisfy some list of axioms. So some of you know what a chain homotopy is, I assume. If you take a simplicial homotopy and take sort of the alternating sum of the maps induced by these HIs, you get a simplicial homotopy. Yeah. Okay, so the next few slides is going to be about like, hey, where does this formula come from? Right, because like in an analogy with simplicial homotopy or with chain homotopies, it might make sense that you want a homotopy to be a degree shifting map, but how do we guess that this is the right formula? G never appears anywhere, so this is not the right formula. I copied it from Wikipedia wrong or NLab. Okay. G should appear somewhere here. Am I missing something? If like, I bet, what's the most extreme case? D. Probably I'm missing D. What's the DN? Yeah, N or N plus 1. No one, I can't think of the board. This is probably G. I probably forgot to copy that down. Yeah. Numbers right. Yeah, I bet this is an N plus 1. Maybe it's an N. Someone feels strongly. But yeah, I'm definitely missing some condition. Like, look it up on NLab. If you want to use something, look it up. Okay, but the point is that there's a conceptual, a more conceptual definition of what a simplicial homotopy is. If you want to write down a formula and check that it's a simplicial homotopy, then this giant thing is actually what you might actually be what you want. But yeah, okay. So yeah, so why are simplicial homotopies useful? So the proposition is that if you have maps of simplicial spaces, then if you the simplicial homotopy gives you a homotopy between the maps on geometric realizations. So in particular, if there is a simplicial homotopy between F and G, then there's an actual homotopy between the maps on geometric realization. Yeah, so that's what we want. Okay, so yeah, so our goal is to to show that these two maps are homotopy inverses by constructing homotopies between their compositions and the identity. And the sub goal is to understand the the formula for simplicial homotopy more conceptually. Okay, so recall that if you have a simplicial complex and you pick an ordering on the choice of vertices, then you can build a simplicial set associated to that simplicial complex, and the p simplices of this p simplices of this simplicial set are just the set of maps from p simplex into X that preserve the order on the vertices. Yeah, so basically the set of p simplices of the simplicial complex X will be the set of p simplices of the simplicial setification of X. And this remark about order preserving, well, if you took, this is X, then somehow there are two non-degenerate maps from an interval into X, but only one of them is order preserving. So if you want the non-degenerate simplices of X, sorry, I said the simplices will agree, the non-degenerate simplices of this will agree with the simplices of X. So yeah, so if you just took all maps, there'd be four things. There'd be this interval goes to the left vertex, the interval goes to the right vertex, and the two simplicial bijections of an interval to itself. We only want, if you pick an order on X, you can say take the order preserving one. So then you only get one non-degenerate, one simplex. Yeah, so we talked about this construction a while ago, and the nice thing is that geometric realization is isomorphic to X as simplicial complexes. Manuel said, hey, if you don't like the ordering, you can, there's some other construction, and it will canonically output the barycentric subdivision of X. That's something you can also do. Okay, so the maybe the more conceptual definition is a simplicial homotopy from F to G is a simplicial map from X across our simplicial model of the interval. So 0, 1 has a natural simplicial complex structure. Turn it into a simplicial set. Take the level-wise product. So the product of simplicial spaces is just take the product on p simplices. So a simplicial homotopy is just the data of a simplicial map from here to here, such that when you include X into the left, this composition is F. When you include X into the right endpoint of the interval, the composition is G. And then, if you unwind what all of this means, it ends up, instead of just like one simplicial map from X across an interval, it's actually the data of a bunch of maps from X to Y degree shifted that satisfy axioms. That satisfy this giant formula, except I forgot G. So, any questions? Maybe this should really be like a prop. This is equivalent. this, maybe really this is a theorem, that this is equivalent to the other definition. Okay, so as I said, one of the compositions is already the identity, so we don't have to do anything there. But the other one is not. I should have flipped the order on the slides. Yeah. So if you multiply everything and then apply the unit, you sort of somehow take all all of the stuff and shove it to the right. And again, this is maybe here I'm assuming the monad comes from an operad to have this make sense. Okay, so but we can just write down a formula for a simplicial homotopy. So what do? We need p+1 maps, and we need, and I guess we have p+1 slots, and you just sort of add a 1 in the ith spot. By add a 1, I mean you use, maybe these are operatic coordinates, but it's like we, I'll write in text. Yeah, so we want, so I guess it's like H0, H0 is like we're saying, well, this equals like identity M, 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 A, and then we can just use the unit to get 4 M's, H1. We're saying, well, view this as M identity MMA, and then use the unit to get 4 M's, etc. Yeah. So then the claim is that these maps assemble to form a simplicial homotopy between the identity on the bar construction and this multiplication map composed with the identity map. Yeah, so the, I guess the slogan for this kind of argument is like it's an extra degeneracy. So yeah, so in general, if this left M doesn't need to be equal to the middle M, this could be some arbitrary right M functor. And so then this H0 wouldn't make sense. So all these, I guess, higher HIs are just the degeneracy maps, but we have this extra one coming from the fact that we plugged in an M here. Yeah. Okay. Any questions? I'm not going to check that this, that this is the identity, but it's probably just like the unit axiom or associativity or something for the monad. Okay, yeah. So then our corollary is that we have natural homotopy equivalences between A and this bar resolution. So this is yeah. So the upshot is this is a way of replacing A by this simplicial object, and this is nicer because level-wise all the p simplices are free. Free means of the form mx. So this is a functorial free resolution of A. Okay.
So you're not gonna check that that H is a homotopy?
I was not planning on it. It's just going to be.
Yeah, I don't see how we meant to interpret that as. Like I don't.
So you'd probably want to check it this way. Yeah. So I mean, like, I think with this formulation, it's probably not that hard. I mean, it's time consuming because there's like eight conditions, and I missed one, so at least 9. G doesn't appear here, so maybe there are 10 conditions to check. But each one of these, if you just sort of write out what these conditions say, is going to be just sort of like one of the axioms of a monad.
Okay, I see it. So the point of that is that you could just like go one by one and check that works. And
yeah. So the more interesting thing to do is probably checking, so I guess there's this proposition that says that if you have if things are simplicially homotopic, then that realizes to an actual homotopy. So the way you would prove this is by using this second definition. But in the second definition, it's, I guess, more obvious that a simplicial homotopy realizes to a like actual homotopy. So if you wanted to fill in all the details, probably what you'd do is you'd first just check that this definition of simplicial homotopy agreed with the other one. By writing out like, hey, what does it actually mean to have a map from here to Y? And so probably the most interesting thing that I'm not doing is checking that these two definitions agree. Because I think it's easy to see that this definition of homotopy will realize to an actual homotopy, and it's easy to see that the formula for H that I wrote down will be a simplicial homotopy in the sense of the first definition. But so does that address your?
Yeah, you can keep going. I just reading that, I had no idea how to go about checking that, and you gave me kind of a sketch of how to
I think you just like write each of them down one by one, and it's going to be it should just be like from the axioms.
No, I just wanted a broad idea of how to get to like from point A to point B, and that's what you said. So,
okay, so then we get that this thing is this free resolution. Because we have these two maps, and the one of them composes to the identity, and then the other one composes to something homotopic to the identity. Okay, so I guess if we go back to what we're trying to do, so I guess we've accomplished this step, and now all we're going to do today is talk about that step. So where are we? So the key proposition that we'll fill in what's written in red is that if you have a map of simplicial spaces, and if each and the map on the space of P simplices is a homotopy equivalence for all P, and if some conditions are satisfied, then a map on geometric realizations is a homotopy equivalence. So so again, for if your simplicial spaces are simplicial are actually just simplicial sets. So if all these XPs are discrete, then in fact, there's no condition you need to check. And this is because this is just the statement that it's a isomorphism of simplicial sets. But if you have simplicial spaces, then this is a non-trivial thing. And the corollary, let's see, do I have the proof written down? Yeah, the corollary is going to be this step 2, that this free resolution is equivalent to this two-sided bar construction, where on the left we instead plug in loops and suspension n. My parentheses are not in the right place. It'd be better if this one were here. So yeah, so the idea is that scanning tells you that Cn tilde Cn x is equivalent to omega n sigma nx whenever x is connected. And so then so the space, scanning tells you the space of p-simplices of the thing on the left are equivalent to the space of p-simplices on the right. And so then you just need to know that if you have an equivalence on, if you have a map of simplicial spaces and it's an equivalence on the space of p-simplices for all p, then it'll be induce an equivalence on the geometric realization. Oh yeah, and so I'm not going to prove that everything here, so you maybe wouldn't have noticed if I had lied, but you need by homotopy equivalence, I really mean what's called a weak homotopy equivalence. So it induces an isomorphism on homotopy groups. If everything you're dealing with has the homotopy type of a CW complex, then that's equivalent to saying actual homotopy equivalence. But if you have stupid spaces like the topologist sine curve or something, then really all I'm proving is really you should replace homotopy equivalence with isomorphism on homotopy groups for all choices of base point. Yeah, but I'm gonna be sketchy here, so it possibly won't be completely clear where that shows up. Okay, yeah, but so this proposition is gonna finish the second step for us, but I'm going to, at a minimum, tell you what's in the red and maybe what the red thing really is, and maybe hopefully motivate that a little bit. Okay, so we're going to need the definition of a cofibration, which is dual to the definition of a fibration. So, what's a fibration? It's like a map E to B, such that if you have a map from like some space, some CW complex X cross an interval into B, and then you have a lift at time 0. So this map is just inclusion into the 0 component, or sorry, this is like inclusion into X cross 0. Then you can lift. So it's like if you have a family of paths and you pick a family of initial conditions, then you can extend to a family of paths, E. Yeah, so a cofibration is you just take this diagram and you dualize it. So the way you dualize Cartesian product is dual to maps. So yeah, so what does it say? So I from A to B is a cofibration if you have a map, if whenever you have a map from A into this mapping space, and you pick a map from B into this mapping space. So basically you pick you have a map from B into X, which you can think of here maybe you should think of X on the you should think of X as like maps from 0 into X. So this is saying if you can, I don't know what it's saying. If you have a map from B into this mapping, you know, so you, for every point in B, you know where 0 goes, and for every point in A, you know the entire path. Well, then you can, then this F tilde exists, so you can extend all of the yeah, you can extend all the initial conditions to paths. So cofibration is some sort of homotopy lifting, and this is homotopy extension. And it, you know, it's just formally dual to being a fibration. I don't know if I can draw a picture of it. So if you think this is a picture of B, and then I guess red is A, and then I guess it's like for each point in B, each point in A, you get some sort of path in X, and then for each point in B, you get a point in X, and then it's saying, hey, we can extend to, for each point in B getting a path. And I guess one thing is if it's going to need to be injective, because if let's say if 2 points in A go to the same point in B, then you can, you know, let's say, you know, then you could just over here you could pick the paths to be different but start at the same point, and then there would be no way to extend the things here because you know, it would have to be both, you know, the extension in both points. Yeah, okay, so you know, you should sort of think of like fibrations, assuming the fibers are non-empty, basically have to be surjective. This maps basically has to be injective. And you know, if you're like, hey, I don't like this formula, what you should just think of is that if you have a sub-CW complex, then the inclusion map is a cofibration. Yeah, I mean, this is, you know, if you understand the diagram for fibrations, you should be able to understand the diagram, this diagram. But you know, sometimes like lots of people like rings, but most people don't like co-rings. You know, people like algebras, they don't like co-algebras, even though it's just you take the diagram and formally dualize everything. Manuel likes co-algebras. Okay. Any questions? Yeah, so this definition is going to be used for making rigorous what this red condition is. Okay. Yeah. So let's sort of, you know, recall what geometric realization is. So you take this space of p-simplices and you cross it with an honest p-simplex, and then you mod out by this equivalence relation involving the face maps and the degeneracies. Okay, so what we're going to do is we're going to describe the geometric realization in terms of iterated pushouts. So yeah, so the pushout of you know, so if you have a map from A to B and a map from A to C, then the pushout is going to be, well, it's like the union of A. Sorry, it's the union of. This is a typo. I guess this is be a C. You know, is the union of disjoint union of B and C, modulo the equivalence relation that things in the image of, like if you point in A, it maps to B and it maps to C, and you just identify those 2 points together. So you start out with A here, map it down here, or map it over there. You just glue those 2 points together in the push out. Yeah, and it satisfies whatever universal mapping property it should satisfy. So here are some examples. So if you take the push out of a, let's say an n-1 sphere mapping into an n-disk, and an n-1 sphere mapping to a point, then the push out is going to be an n-sphere. Because what we're saying is it's going to be, d cup, it's going to be over Sn-1. So what are we doing? We're identifying, so you take the sphere and a point, but then you identify you take a disk and a point. We got this point, but what you do is, you say, okay, I got my sphere, and let's say this point on the sphere is going to map to that point here, but it's also going to map to that point here. So you're gluing this point to that point. But hey, this point on the sphere, I don't know, it's going to map to that point on the disk, but it's going to also map to this point. So you're gluing this point to that point, but then hey, that has the effect of you're gluing this point to that point. So the end result is you collapse the entire boundary of the disk to a point, and you just get an n-sphere. Any questions? And now in this example, the push out is going to be, well, a point, disjoint union of points. So we have at most 2 points, but then modulo the image of modulo like something in here. The image of something in here is identified with its image over there. But you pick a point in here, it'll map to here and here. So these 2 points get identified. So the push out here is just 1 point. So yeah. So in what way? Yeah, so I guess here, so what I'm saying is that disk push push out with n-1 sphere of a point is Sn, and down here I'm saying point okay, so these two pushouts, the end result is spaces that are different, different up to homotopy even. Is there any reason why you might have guessed that these two things should be the same? I mean, they're not the same, so you shouldn't really guess that they're the same. But what is similar about?
Because dn is contractible.
Yeah, dn is contractible. So if you say, hey, like, what are the spaces that we've formed to push out here, and what are the spaces we formed to push out here? Up to homotopy, they're the same. 2 contractible spaces and an n-1 sphere. But if you take the push out, you get different things. So, I'd say like, hey, this is annoying. How do I know when pushouts will be homotopy invariant? And then the proposition is that, if you have Maybe I should have written the F prime version. You know, if you have the push out, if you're taking the push out of like F map A to B and G to C, from A to C, and similarly F prime like this. So you know the then I guess yeah. So if you have these two push out diagrams, you're going to get a homotopy equivalence if like one of F or G are going to be cofibrations. So if like F and F prime are cofibrations, then the then what you get is going to be homotopy invariant in the sense that if you have these maps that are compatible, you know, if you have maps from A to A prime, B to B prime, C to C prime that are homotopy equivalences, and like let's say the Fs or equivalently the Gs, I mean it's completely symmetric. If one of those pairs of maps are cofibrations, then the induced map on pushouts is going to be a homotopy equivalence. I feel like I need some conditions for. Oh, I guess I said making the whatever diagram commute. Yeah, if you just had maps like this, it's not going to necessarily induce a map on the pushouts, but yeah. If whatever diagram you can write down commutes, then you'll get a map on the pushout. Yeah, so here, this map is a cofibration. You know, the bottom map isn't, but who cares? And but then in yeah, the purple one is a cofibration, and the but none of the red ones are. So that's why the pushouts aren't homotopy equivalent. But you know, if you make, you know, let's say go back to purple. If you replace this dn, say with, I don't know, you just plugged in you know, so as I said, like sort of cofibration is some like homotopical version of being injective. So this map is injective, but the map from a Sn-1 to a point isn't injective. You know, but if you can replace, you put your favorite contractible space that includes Sn-1, you know, you could, but I don't know, you know, Rn here, for example, or Rn plus 7, you know, doesn't matter. As you know, so you took sort of a nice, you know, an standard injection into Rn, and then I don't know, included into Rn plus 7 or whatever. Then whatever you got here would have the homotopy type of Sn. Yeah, if you plugged in Rn plus 7, it wouldn't literally be homeomorphic to Sn, but it would have the homotopy type because, you know, you made this purple map into a cofibration. Okay, yeah, so cofibrations are things that are homotopically well behaved with pushouts and similar constructions. Yeah, and so then we're going to sort of reinterpret geometric realization in terms of pushouts. Okay, so yeah, so let me talk about the skeletal filtration. So if you have a, you know, if you have a simplicial complex or simplicial set, you know, let's say you have a simplicial complex, you probably know what the 3 skeleton of a simplicial complex is. So we're trying to just write down the analogous definition. So the D skeleton is basically you write down the formula for geometric realization, except the key thing is that you only take the space of p simplices cross p simplex when p is less than or equal to d, and then you mod out by the same relations, and you know only apply these equivalence relations when everything is in your subspace. Okay, so yeah, so this construction, I mean, gives you a space, and then it says if you know, if you started out with a simplicial set, then this will just give you what you traditionally think of as the D skeleton. And so you probably we're told at one point if you take the D skeleton and you mod up by the D-1 skeleton, well, like what do you normally get? You normally get a wedge of spheres. But that so and the spheres are indexed by all the D cells of your space. Well, this proposition generalizes it to simplicial spaces, so it says that if you take the D skeleton mod the D-1 skeleton, you get a suspension of the space of D simplices. So if you have a simplicial set, then this would be discrete, and then this would just be a wedge of D many spheres. But if the space of if your space of D simplices has topology, then you think of this as just then the correct way to topologize it is just say xd suspended d times. Okay, so then we're going to define this the latching object, the D latching object, as the image. So you take the space of D-1 simplices, so these SIs give you the degeneracies give you maps from the space of D-1 simplices, the space of D simplices, and this LD is just you take the image of all the degeneracies and union them in XD. And then we call a simplicial space proper if all of these, the inclusion of the latching object into the space of D simplices is a cofibration for all D. And so, okay, so why do we care about these latching objects? Well, the D-1 skeleton is a push out of the space of D simplices cross an actual D simplex is a push out over some complicated thing involving latching objects, whose formula, I don't know if I wrote it down correctly, and I've not internalized myself, but the proposition is basically that if that if you're proper, then this this map here is going to be a cofibration, which basically will let you using that push-outs along cofibrations preserve homotopy equivalences will let you prove that that geometric realization is homotopy invariant each skeleta at a time. So you're comparing. I guess we're trying to prove this proposition. And the way we're going to prove that is by, well, we're just going to prove that the D skeletas are homotopy equivalent for each D. And then the way we would do that is we would say, okay, we have this map that induces a homotopy equivalence on the space of P skeleta. So let's assume by induction, our hypothesis tells us that it's going to be a homotopy equivalence on this factor. And by induction, we can assume it's a homotopy equivalence on that factor. And then basically, we want that it's a homotopy equivalence on that factor. And we use that cofibrations. If you have that push-outs are homotopy invariant, assuming one of the maps is a cofibration. Okay. Yeah. So and then you use this proposition to prove this. You have to check that both of these simplicial spaces are proper, and it's somewhat technical. And Zach, do you actually know how this proof works, that these things are proper?
No.
Okay.
Yeah, I don't know.
It never seemed interesting enough for me to. It seemed technical. I wrote a paper where like I declared things like this were proper, and I said, "Oh, just read geometry iterated loop spaces. The argument there goes through here," and the referee accepted that. But yeah. So you check that these are proper, and then the interesting thing is that the interesting thing is that the reason why they're a level-wise homotopy equivalence is because of scanning. But then the technical thing is why the level-wise equivalence will imply a homotopy equivalence on geometric realizations. Oh yeah, one other thing to say is that there's this thick geometric realization. And so there's two other propositions. So if f, let's write star. So if f star from xp from, if this is a homotopy equivalence for all p, then you get a homotopy equivalence on thick geometric realizations. Without any assumptions. So that's one way in which the thick geometric realization is nicer. There are other ways in which it's not nicer. Like all of these things are going to be algebras or little disks operad if you take the thin realization, but I think if you take the thick one, it won't be. If that's wrong, someone can correct me. But yeah, but one thing that is true is if x star is proper, then there's a natural map from the thick geometric realization to the thin one, because the thin one is defined as a quotient. The thick one, you don't mod out by the image of degeneracies, you just mod out the equivalence relation involving face maps. So if your thing is proper, then the two geometric realizations are equivalent. There's another proposition. If x bullet is a simplicial set, then x bullet is proper. So this condition about being proper is vacuous for simplicial sets. I think if you think about it, it's just going to be that an injective map of sets is a cofibration. What'll end up being relevant. Yeah, okay, so this gives us this corollary, modulo some technical things. Oh yeah, so maybe yeah, so all that remains for next class is to prove that if you have a is to do the last step. So basically, we just need to pull loops out of geometric realization. So, we're going to prove that if each xp is path connected, then the geometric realization of loops is the same as loops on geometric realization. And the corollary will be the last step, and that will say, that this En algebra is loops n of something. Okay, yeah. I'll stop the recording, but if there are any questions, I'll stick around.